Hello friends, welcome to today's lecture Stresses in Beam. Myself, Mr. Y. S. Patil, Department of Civil Engineering, Shear Institute of Technology, College of Engineering, Yadra. In last lecture, we discussed about shear stresses in a symmetrical section. Now in this lecture, we discuss about shear stress distribution for unsymmetrical section. So let us see one problem on the T section. A shear force acting on a section of beam 50 kN. The section of the beam is T-shaped of dimension 100 mm by 100 mm by 20 mm as shown in figure. The moment of inertia about horizontal neutral axis is 314.221 into 10 raised to 4 mm raised to 4. Calculate the shear stress at the neutral axis and junction of the wave and flange. Before starting the solving problem, we calculate the neutral axis distance. That's why you want to calculate y bar of the section. So this is a T section. This T section split up into two rectangles. That is, this is the first rectangle having dimensions 100 by 20 mm, and this is the second rectangle which dimension is 20 is width. Now 100 mm is given overall depth, so wave depth of this particular wave is 80 mm. So calculate y bar is equal to a1 y1 plus a2 y2 divided by a1 plus a2. Now section number 1 becomes 100 by 20, so this is the a1, and y1 is distance of section number CG of section number 1 from the top side. That is, this is the 20 divided by 2 is 10. So this is the 10 mm from the top side of the section. Second, section number 2 is 20 by 80 mm. So this is the A2. Now we want to calculate y2. Y2 for CG for this section number 2 is 80 by 2. This is 40 mm. But we want to calculate CG from top of the side. That's why we want to add this 20 mm. So y2 becomes 20 plus 80 by 2 divided by a1 plus a2. By calculating these all values, we got y bar is equal to 32.22 mm, and that distance is 32.22 mm measures from top side. So this is the y bar from top side. So overall depth is 100 mm. So remaining distance is 100 minus 32.22. It becomes 67.78 mm. So this is the simple procedure to calculate neutral axis distance. Next, Q1. At top and bottom of the section, the shear stress value becomes 0. So there is no need to calculate that value. Directly we go to Q1. Q1 means at the junction of flange and wave. So when you calculate Q1, the equation of the shear stress is SAY bar upon BI. Already shear force is given in the problem, that is 50 kilonewton. Then moment of inertia also given in the problem, that is 314.221 into 10 raised to 4 mm raised to 4. Means this S and this I value is a constant for all shear stress values. Just variables are A, Y bar and B. So let us see what is the A value for this Q1. For this Q1, the A value is considered above this junction area. So above the junction area is 100 mm by 20 mm. So area becomes A is 100 by 20 mm. Then y bar means CG distance of that area from the neutral axis. CG distance of that area from neutral axis. Suppose this is your CG value for this particular area, then this is your y bar. Okay. Now B is equal to 100 mm. So all, now we know the all values, that is we know the S value, we know the A value, we know the Y bar value, then we know the B value, we know the I value. So Y bar, now this is a 20 by 2, this is the CG of this particular area, means 20 by 2 is a 10, and we know the overall depth of that neutral axis from the top side, that is 32.22. so means this Y bar is 32.22 minus 10, that is 22.22. so Q1 becomes 50,000 into 2000 into 22.22 divided by 314.221 into 10 raised to 4 into 100. By solving this equation, we get 7.07 Newton per mm square, and that value is a Q1, that is shear stress at junction. Then next, calculate Q2. Q2 is much easier calculating shear stress at Q2. How to calculate Q2? Shear equation is Q2 is equal to Q1 into B1 by B2. B1 by B2 means what? Width of the top flange divided by width of the whip. This is the B1 means flange width, B2 means whip width. So Q1 is equal to 7.07. Now B1 is 100 mm and B2 is 20 mm. So B1 by B2 into Q1 is 35.35 Newton per mm square. This is the value of Q2. Now we calculate this Q0 value, Q1 value, Q2 value. Now I want to calculate Qmax. Qmax means already we discussed the maximum shear stress acting on the neutral axis. So we want to calculate Qmax or QNA, maximum shear stress acting on the neutral axis. So QNA or Qmax. So QNA is equal to Q2 plus Q additional. Already we calculate Q2. Now we want to calculate Q additional. How to calculate Q additional? By considering this additional area. What is my additional area? Above the neutral axis and below the bottom of the flange. So what is the depth of this? What is the depth of this section, additional section? That is, this overall is 32.22 minus this depth of the flange, that is 20. So it becomes 12.22 and width of the section is 20. So area becomes 244.40. Now Y bar for this particular section is, the depth of the section is 12.22. So Y bar becomes half of this 12.22, means 6.11 mm. 6.11 mm. This is the Y bar of the section from the neutral axis. So Q additional becomes SAY bar upon B into I. So S becomes shear force, that is 50,000 into area is 244.40 into Y bar is 6.11. I is a 314.22 into 10 raised to 4, and B, now width of the section for this particular section is 20. So Q additional becomes 1.18 Newton per mm square. So you got the Q additional, and Q neutral axis QNA or Qmax is equal to Q2 plus Q additional. So we know the value of the Q2, that is 35.35, and we calculate that Q additional, that is 1.18 Newton per mm square. So adding this 35.35 plus 1.18, we got 36.53 Newton per mm square. This is the QNA. Now we plot all values and we draw shear stress distribution diagram. Basically, this is one vertical, draw a vertical and reference line. At top and at bottom of the section, shear stress value becomes 0. Then at Q1 is 7.07, Q2 is 35.35. Draw this by using parabolic curve, first 0 to Q1, and Q1 to Q2 it is junction stress, so it moves horizontal straight line. This is the Q2 value, that is 35.35 Newton per mm square, and we know the value of the QNA, that is 36.53 at a distance of 32.22 from top of the side. Plot this 36.53 and draw a parabolic curve. Now from that neutral axis to the bottom of the section there is no shear stress value, so join with 0. So this is the shear stress distribution diagram for T section. At neutral axis we got maximum stress, at the top and bottom it will be 0, and at junction we got two values, that is Q1 and Q2. So this is the solution for shear stress distribution for T section. Thank you.